Dear fellow coders, welcome to Untitled Coder. This is day 19 of Kaggle's 30 Days of Machine Learning Challenge. So far, we have been discussing about machine learning explainability. And in this machine learning explainability series, we have seen about permutation importance, partial dependence plots, and we have also learned a little bit about SHAP values or Shapley values, how it can help us in identifying local interpretation, which is like you take a particular data point and that for that particular data point you understand why such a prediction has been made. So to quickly summarize what we have learned in SHAP values, SHAP values. SHAP values show how much a given feature, a particular feature, has changed our prediction. So compared to if you had a baseline number. For example, let's take this equation for an example. So y is equal to 4 into x1 plus 2 into x2. So if you see, if x1 takes the value of 2 instead of a baseline value of 0, then our SHAP value for x1 would be 8. So basically what SHAP value does is, so you have two things. One is your baseline value and the second one is your actual value. So what SHAP value calculates is, what if you did not have the baseline value, and for the current value, what would be your SHAP value? So if you see this chart, like the plot interactive graphics that SHAP value gives, you can understand from this chart how much is the base value. For example, here you can see base value and the actual output value that you have got, and you can also see how much the predictions have been changed. So everything that you see on this left hand side, which is like the pink color, it's a driving prediction, like higher prediction, and everything that you see on the blue side, it's driving prediction on the lower side. And you can see the width that you see, that is like how the magnitude of the change, which means the most important variable. The smaller the magnitude of the change, you can say lesser the variable importance is. The larger the magnitude, you can say larger the effect of that particular variable is. So now that we have quickly recapped what we learned about SHAP value, and it's quite easy to implement SHAP value. You would have seen that we had a library for SHAP value, and then just a couple of lines of Python code, we implemented SHAP value. Now that we know what we have done with SHAP value for local interpretation. So again, if you do not remember, so there are mainly two kinds of interpretation. One is local interpretation, the other one is global interpretation. Local interpretation is where you take a particular data point. You just take one data point and you understand why such a prediction has been made for that particular data point. But if you see, let's say permutation importance on the other hand, it talks about global interpretation. On an overall level, how is the model performing? Or to be specific, on an overall level, what are the features that that let's say has importance? So that's what global interpretation is. So now what we can do with SHAP value is, there is a concept in SHAP value called summary plots. So what is summary plot? Summary plot is a way for you to aggregate all the individual SHAP values and then take it to a level up, or take it to a summary level that can give you global interpretation. Let's see why is it even required in the first place. For example, if you take permutation importance as a case, permutation importance is really good because it gives you numeric way, like simple numbers to understand what are the features that mattered most to the model. Like for example, in this case, if you had built a permutation importance, you would have probably seen like gold scored has some kind of value that says like, oh, gold scored is like this X% or X much important to the model. Like you get that kind of, interpretation or numeric measure that you can do a lot with, like even share it with your business stakeholder. But what it doesn't tell you, what permutation importance doesn't tell you, is how is such a thing. Like for example, let's say that a particular feature has medium importance. For permutation importance, let us assume that a particular feature has medium importance. This could mean two things. One, it is possible that a large effect for a very few predictions, like that particular variable has a large effect for very few predictions, but no other effect in general. Which means like maybe that particular variable has large effect for very few, like for outliers, but in general, like on an average, you don't see anything. That's why you see medium importance. Or in general, for every single prediction, it has medium effect. So it could be either of these two. So, but if you want to further dig in, permutation importance doesn't give you that ability or flexibility to further drill down into the data. And that's what your SHAP summary plots give you. And like I said, what is SHAP summary plot? You take all the individual SHAP values that you predicted or that you calculated, and then just make a summary chart out of it. Take a look at this chart. If you take a look at this chart, there are a lot of components in it. Let's talk one by one. Let's talk about one by one. So first of all, in the x-axis, you would see the SHAP value, which is basically the impact on the model output. So that's your x-axis. On the vertical axis, you would see all the variables, right? All the variables are there. On the right hand side of the vertical axis, you would see the feature value. That's a color code that says whether the feature was high or low for that particular data set. And now you have your left axis is sorted, your right axis is sorted, your x-axis is sorted, and you would also see that there are multiple colors here. And these colors are assigned with this. Like for every data point, you can actually see what is the value mapped here. So this color is mapped to your right axis, your left y-axis is the variable name, and your x-axis is the actual SHAP value, the horizontal axis, which basically says whether the effect had like increased the prediction, higher prediction or lower prediction. That's what basically you say. So if you want to read it, like for example, goal scored. If you see goal scored is the most important variable, like you can understand from this, because you can see it is mostly on the higher side, you can see. And if you want to see some other variables, you can say, oh, red, yellow and red, model just completely ignored it. Model didn't care about these features. So basically it doesn't matter much. It doesn't make a big difference if you have this variable or if you do not have this variable. So just simply looking at this plot chart, you can make this case that okay, I don't need yellow and red, or I don't need red variable. So that is done. If you look at another variable, which is yellow card, in this case, you know that yellow card in general doesn't affect prediction much, because see, again you can see it's closer to the middle line, like it's closer to 0, it doesn't impact. But you can also notice there is one very high value on the left hand side, like somewhere, in extreme case, high value because of this color, and it is on the left side, which means it is lowering the prediction. So in general, yellow card doesn't make much impact on the model, but there is one extreme case that drags down the prediction, like that causes lower prediction. And also high values of goal scored cause high prediction, low values of goal scored cause low prediction. Blue color, low. The one, like let's say purple and pink, high. So just looking at this plot, you can make sense of this. You can come up with insights that can help our business to understand what is going on in terms of the variables, not just a variable importance plot, but also have the ability to express like what is happening with the individual cases as well. So this is the first example of how you get global interpretation, or a summary plot that is similar to permutation importance, feature importance using SHAP. Now let's look at the code section. The code is quite simple. So just to give you a quick refresher about the code that we have been looking at: NumPy for numerical computing, pandas for data manipulation, train test split for cross validation, random forest classifier for the machine learning model that we are building. We read the data inside, we're converting the string data into binary, true or false, and we are extracting the target variable, and then we are extracting the x variables, like x data, which are the values that we are going to, explanatory variables that we are going to use to predict y. And finally we are going to do train and test split, and then you define the model, random forest model, and then you also fit the model. Now at this point we have got a working random forest model in place. Now our objective is, can we take this random forest model and then say, okay, these are the features that are important for this model. This is how such a prediction has been made. For that, we have to import library SHAP, SHAP, and then very nicely SHAP has a tree explainer. Like even in the previous section, you might have already seen this thing. So SHAP has a very nice tree explainer. Once you create the object explainer, which is from SHAP.treeExplainer, the input it takes is your model, then you can actually give the validation data set for it to calculate the SHAP values. So first you have the explainer, like what kind of explainer you want to build. In our case, because we have got a random forest classifier, we need to build a tree explainer, and after that you calculate the SHAP values, and finally you plot the SHAP values. So you take SHAP values of 1 and then you plot it with the validation data set, and you get this exactly. Now you might think, oh, what is this? Why am I calling SHAP values of 1, right? That's a valid question. Like, what does it contain that I have to say SHAP values of 1? So when you run this step, which is SHAP values is equal to explainer.SHAP values of the validation data set, this actually contains two elements. One is the SHAP values for a false target variable. Like if you look at the target variable, it can have two values, right? It can have either true or false. So the first one, which is like the 0th element, contains the SHAP values for false cases, and SHAP value of 1, which is the first element by index, has got the SHAP values for true predictions. So one is for false, second one is for true. If you remember decision tree, we had a very similar situation in decision tree as well. So next important thing that you have to notice, SHAP values are very expensive, computationally very expensive. In this case, we have got a very small data set, so it was easy for us to plot it. But you have to be very mindful if you have got a very large data set, because that can ruin your entire machine learning experience. Of course, interpretability is very important. You need to explain this, but you can always come up with an alternative solution, because you don't want just your interpretability code or one line of Python code that creates a nice chart for you to explain the model for like very long hours. It might even, like break your machine. So do SHAP when your data set size is small, and if you do not have such a data set size, come up with alternatives. Another good way to use SHAP is when you use XGBoost. SHAP has got a couple of optimization options, and I guess there is an add-on, or there is an extension with NVIDIA GPU where you can run SHAP on GPU. Like there is a function, if I remember correctly. You can always check about it. So this is basically, in a couple of lines of Python code, we have successfully managed to create a summary plot using SHAP, which inherits the principles of Shapley values from game theory that we used for individual or local interpretation, but we just abstract it, or we just summarize it to a global interpretation level. Another important use of SHAP values is not just a simple global interpretation, but you can also make dependence contribution plots. This is very similar to what we did with partial dependence plot, which is what we used to say how much a single feature impacts prediction, how much a particular feature moves the prediction, or like what kind of impact does it have. So this is very, very important if you have like a non-technical stakeholder or an audience. Imagine you work for a marketing department and you build a model, and let's say you're saying that like if you deploy this model, you would get like 97% in accuracy. Now the next important question would be like, what does it mean? Like what does this model mean? Like what is this model doing? So like maybe you want to start a campaign. Like now, how do I know what are those variables? Like how a particular variable, let's say buying power in this example. Let's say how much buying power impacts conversion in a marketing campaign. Like it's a valid question, right? Maybe you want to target your marketing campaign only for those with highest credit score, or you want to do something like that. So this is a very valid question which may not be easy for any non-linear model. Like it could be easy with linear regression or logistic regression, but it may not be easy with any other like model, especially if you talk about ensemble models. And that's where SHAP dependence contribution plot really helps. If you look at this plot, this is how it looks. Again, to quickly show you what is there in the chart, your x-axis is the ball possession, the actual variable. Like for example, it could be goal scored, it could be anything. Your y-axis on the left-hand side has got the Shapley value for the particular ball possession. For whatever that value is with respect to this is the value. And on the right-hand side, you would see the goal scored, which is the variable against which you are measuring the impact, like number of goals scored. Okay, so now that you know what are the components that you have seen in this thing, you can actually see that that if you look at this, these two are on the same y line, right? Like you have the same y line and you can see these two. But even when you see the ball possession percentage, let's say in this case both of them could be like somewhere between 50 to 60%, you can see it has a huge difference in the goal scored, like the value of goal scored. Same thing, if you look at this chart as well, you can see ball possession. It's a very high ball possession rate, like 70% of the time, but it has actually reduced your goal scored option when you compare it with this or any other data point that is on your top right corner. So now this is a nice way for us to make some conclusions, or I shouldn't say conclusion, make some insights about what is happening. Maybe we can say that, oh, in general, when you have the ball for a lot of time, like basically having ball possession increases your chance of getting man of the match or player of the match award. But on the other hand, it is possible that when you hold the ball for a very long time and then you just score only one goal, it is possible that the referees might penalize you and not give you man of the match award as well. So that's why you don't see any impact. Like if you have one data point and then let's say you have also scored goal well, now you can say there is a positive impact on Shapley value. But if that is not the case, then you need to understand that SHAP, like in this particular case, okay, I understand that I've got higher ball possession, but because my goal scored is approximately 1 or less than 2, I have been penalized, or my team has been penalized and not given the man of the match or hire a match assistant. Okay, so basically you get to combine your existing feature with something else. For example, in this case, ball possession with goal scored, and then try to understand how much Shapley value is changed for a particular ball possession value. So that's what your dependence contribution plot, very similar to your partial dependence plot, PDP. So again, you use SHAP, same like before, and you have to use the tree explainer because we have got a tree based model, and then you have got Shapley values calculation. Finally, you have got SHAP.dependency plot instead of SHAP.summary plot. And once you have dependence plot, you can just plot it, and you got exact same plot that we were discussing until now. So to summarize completely, we have learned how we can use SHAP library or Shapley values to calculate global interpretation, which is at a feature level or at the model level, at the overall data set level, that could help a lot for non-technical business stakeholders to understand what is happening. So in this series, we totally learned about, starting from the first, we learned about model use cases for model insights, permutation importance, partial plots, SHAP values, advanced use of SHAP values, and you can try this exercise. So if you finish up this exercise like every other exercise in every single video, then you would get a very nice certificate from Kaggle that you can probably attach it to your profile. But I would say what is more important than having, let's say, a certificate from Kaggle that you can attach on your profile, I would say it is important for you to try hands-on experience. You know the data set, like it's just a couple of copy paste, and then your mindset would improve for you to code. So it's very important for you to do hands-on problems. So please solve the exercise yourself, go to Kaggle, and then start building new SHAP based notebooks that would also help. And at the end of the series, if you finish the exercise, you would get certification, like I said. So we have completely successfully completed our machine learning explainability course. If you have any question, please let me know in the comment section. Otherwise, I believe this course was helpful to you. Stay safe.